Welcome to lesson 4. Today we're going to cover semantic segmentation and custom pre-trained models. Now, what is semantic segmentation? Generally, semantic segmentation is this idea of, given an image, we can create essentially a mask over all the important items. And you can think of a mask as drawing like an outline of a person and then coloring it in all with blue, for instance, in a picture. That is what we would call a mask. And the more proper way to think about it is in semantic segmentation, every pixel in an image is defined as a class. So for example, that could either be binary, where it is a person or not a person, or it can be multiple classes or multi-class, such as here's pixels of a cat, here's pixels of a dog, and here's pixels of a person in a family portrait. In Jeremy's course, the latter was shown through the CamVid dataset. In this course, though, we're going to cover binary segmentation because it's a bit trickier and introduces one of the most common bugs that exist when you're dealing with semantic segmentation in PyTorch and in fastai. Now, for this example, import vision all, the exact imports will go in there later today because we are dealing with computer vision. Now, the dataset for today will be different. We're actually going to use a dataset of portraits from a Kaggle competition. So in order to run and download it, especially if you're using Google Colab, is to run pip install gdown, which is Google Drive down. But if you're in Colab, make sure that you add -u to the end of it. Otherwise, you'll get this error saying you don't have permission to download this shared URL, and there's a bug fix patched, and for some reason, Colab doesn't come with it pre-installed. You're going to take the URL and then run a quick bash command to just download it quickly. It'll be stored in a portrait.zip file. Again, remember that this // here is for my own computer because I didn't want it in the same space as a repository. If you're just downloading this top down, remove this // as well as this // data. Now, if we look at what is in the data here, now the repra I'm printing here is pathlibs repra, and it's to make it a bit easier to read. And then I'm also going to check if it's a file or not, or a folder. That is the only two differences that's happening here. So we can see that we have a file called images.csv. We have a folder called images compressed, a folder called images original, a folder called images data crop, a text file that's train and validation, some interesting EG 1800 train and validation, and the ground truth images. So the main two text files we're going to care about are train and validation. We're not going to worry about this EG 1800. That's not really relevant to what we're doing today. So let's go ahead and explore our data. So if we look at one mask of labels, this is the ground truth PNG. So we're just going to grab one of the masks. This is what we're looking at. So you can see the binary segmentation happening here where the background is probably 0 and the foreground here is 1, and there's nothing else in here. And with semantic segmentation, as I mentioned earlier, the labels are a 1-to-1 pixel match with the original image. And let's go ahead and take a look at the labels because it's going to be just an array of basically row by row the pixels of 0 to whatever our total amount is. And you'll notice they're not floats here. They're integers because in this case, we don't have partial classes like that. Now, very quickly, I'm going to point out an apparent issue with these masks. When using fastai and calculating the loss function, and generally in PyTorch as well, you could certainly try to start training without pre-processing and going through the steps below, without really paying attention much to, oh, this is 255 and this is 0. But what winds up happening is you'll get an error later on that says CUDA seg fault index out of bounds. And essentially what this means is with how fastai calculates the losses and the metrics, and generally in PyTorch as well, these numbers, these class labels, need to be arranged from So if we attempt to get back to where I was at, basically when we calculate the loss function, you're going to get a seg fault if all of the class labels don't align from 0 to n minus 1, right? Your number of classes. And so here we have nothing in between 0 and 255. And on top of that, the vocab in fastai is set to, in this case, it would be 0 to 1, right? Because there's two classes. That would make sense. And so you'll get a seg fault because it's trying to find a class label for 0 and 1 when 255 is nowhere in there and the model can't do 255, right? It's set to print out, or it's set to predict two classes, not 255 classes. And that's where this index out of bounds happens whenever it's trying to update those weights. So how do we fix this? Basically, we create a small pre-processing function here that contains a set of our unique codes. And then for every file name in our files, we're going to open the mask, convert. So in order to deal with this CUDA device assist error, we're going to need the get codes function here, which helps us convert the pixel values. Do we have audio again? Oh, yeah, I took a long pause. And essentially what this will do is it'll get a dictionary of the original code in the, well, this is backwards. It should be new code by original code. And so what this will do is create a set for every file in our file names. We're going to open the mask and convert it to a NumPy array. NumPy then lets us get the unique values from it. And we're going to add this to our set. So essentially what this allows is if there's rare classes in your data set that don't show up in the first n file names, you can still get through and get all of them and make sure they're part of the vocabulary. And then this will return that dictionary of the new code by the original code that we can use to translate the pixel values. So this is just using the first 20 images. And we can see that after we replace our values, which in order to do this legally, it used to be easier, we need to use this numpy.place on a copy of the mask. It's really weird how NumPy makes you do these things now. It used to not be this way. It used to just be able to do mask at this location, convert it to that, but they don't allow that really anymore. So this just simply looks at our mask, goes, okay, everywhere it's 255, change that value to 1. which we could rewrite this as iterating through all of our unique codes, finding all of the mask values that are that value, and changing it to what it should be. So next, we need to build the data loaders. So our input is an image and our output is a mask. So we're going to have image block and mask block. On top of this, the mask block will accept a codes list. And the codes list is essentially our vocabulary. So here our codes are 0 will be background, 1 will be face. Next, we need a getY that opens a file name and converts it to the PIL mask and will also replace those values. This is a little different than any getY we've seen before, because typically getY will just return a file name, right, to open it, because PIL mask will open a mask from a file name that we saw a second ago. And the reason we're doing this is we have to do the pre-processing here. Technically, we could write this as a fastai transform. Trust me when I say it's easier to do this in the getY as a preprocessor. Dealing with fastai's transforms to write this, while it might not be a lot of lines of code at the end of the day, keep it simple. Keep it very simple and just do it when you grab the Y, because it's going to have to open it anyways. And then when it passes it to PIL mask, it just doesn't really do anything as a result because it's already a PIL mask. So we can test it works by doing getY, passing in one of our files in our unique codes, and we can do mask.show. Now here you'll notice I have this CMap equals blues. Anytime fastai uses the .show function, it uses matplotlib, which will accept any number of keyword kwarg arguments. I've added a link on the right here for you to go look at what all of those are. But here it's easier for us to see background versus foreground by setting the color map to blues. Now that we have a mask and we've opened it, let's go ahead and create our data block. So we're going to pass in our blocks, pass in the random splitter. For our getY, because our getY we made a second ago takes a file name and a unique codes, we're going to create a partial function that will let us pass in our unique codes as the new default. So now anytime we call getY, it will only need the X, the file name. There we go. It will only need the file name, and unique codes will already be passed in for us. For the item transforms, we're just going to do a simple resize. And then for the batch transforms, we'll do the standard aug transforms and normalizing from ImageNet. One thing to note here is you'll notice I have a batch size of 8. When we do semantic segmentation, and specifically with fastai's UNet, it is a very hungry model. And I'll show you why it's a hungry model in a moment when we look at sort of what it's about. But generally, you're probably not going to be able to train with a batch size of 64 or a batch size of 32 with a 224 image size, unless you have a really, really beefy GPU. So here we're only going to use a batch size of 8, and we're going to use all of the image files from the image data crop folder, which is where this data set exists for us. Now, if we show a batch, we can see the foreground that has our labels and the background that has a label of 0. You'll also notice that our data isn't entirely clean. Like there's some of a shirt from this little girl over here, as well as some of her toy back here. And so, our model might not get 100% accurate because it's going to try and want to label these. And so it might overfit on the wrong labels a little bit there. But we've seen our batch. It all looks right. So now let's recreate that with data sets, because this is going to look a little different. So when using data sets, this part looks pretty average to what you expect. Get image files, PIL image create. We only need the get y here because it creates a PIL mask at the end of it. That's why there's no PIL masks.create over here. And then we apply our splitter to the dataset items. When we create the data loaders, this is where things will get a little different. So we're going to still resize past to tensor, and we're going to add a new transform here called add mask codes. These are those codes that we made a second ago, that list. And what winds up happening is fastai will inject these codes into the metadata of the tensor. And metadata in programming is a whole bunch of complexity. But basically, let fastai handle this for you. I would not recommend investigating that further, just because the whole process is not something I'm even going to prepare you for in this class. Fastai's transforms are really like running with fastai material. I'm going to briefly talk about them from a high level perspective, but running with fastai is essentially going to tell you, here's what they do, here's how they work, don't do it. And then after batch is still going to be aug transforms, into float tensor, and normalizing. And we can look at a batch and see, hey, it works still. So now let's talk about the UNet. Insert scary noises here. Typically with fastai specifically, you will use the UNet architecture. And essentially how this works is we take an image. So say this is an image of 1 by 64 by 64. Then we're going to compress it down by a factor of 2 until eventually we get to this 1024 long matrix that's much more compressed and smaller than the original image. And then we're going to blow it back up to the size of the width and height, and the Y channel, so here was a 1 channel image, is now 2. Because in this example, it's binary segmentation, and each of these channels out here represent one of the classes. So the first channel represent class 0, the second channel represent class 1, so forth and so forth. You'll probably have seen many places where this is used, especially in Stable Diffusion. Jeremy's latest course has a few free lectures that are already released talking about it. Highly recommend watching them. Otherwise, I have linked a video on the side explaining in grave detail how the UNet works. And there's a long description here as well for you, so it's not just in the video. Now in fastai, given there's a learner for every problem, there is a UNet learner because it's different than the vision learner. So there's a lot of configurations that you can add to the UNet learner that I did in the previous walk with fastai that you can read up on if you want to start playing with it. In my opinion, though, the defaults generally work fine. The main two that we're going to be adding is self-attention to the model and changing the activation class to Mish. The main things you'll notice here, let's actually see if it's ready. It is, nice. So if we go down here, the main things you'll notice is, so we're going to pass in the data loaders, the backbone we want for that ResNet, or for that UNet, that's going to be the ResNet 34. For our metrics, we can still use accuracy. However, the class labels and probabilities aren't all in the same channel anymore, right? Each channel has its own class probabilities. So we need to tell the accuracy metric that we want to use the first axes when calculating the accuracy. We do that again with cross entropy loss flat, and this is just what you do for segmentation based on how the labels are being predicted on, right, with each of those singular channels. If you don't pass in axis equals 1, as a student tried earlier, what winds up happening, and we'll try and get as best we can, is you'll see this assertion error exception occurred in recorder when calling after batch. This is some fastai callback stuff that basically tells you in the recorder callback, something happened in the after batch event, which is after the probabilities have been calculated and you're going to calculate the loss. Okay, it says that 3,584 does not equal 400,408. Basically, what this means is we set our axes wrong. So here the axis was set to 0 when it needs to be 1. That's why this one, our input, our prediction, is much smaller than our output. So be sure to set axis equals 1 when you're working with segmentation. Now, I've included learn.summary here, and learn.summary provides a quick glance at the layers in your model, the output shape, and whether or not certain things are trainable, and their param counts. So we can see here that the unit takes in a batch size of 8 of a 3-channel 224 by 224 image. And then through the first section of layers, that gets compressed into 64 by 112, and then 64 by 56, and then 128 by 28, 256 by 14, 157 or 512 by 7 before going to 1024 by 7 by 7. So this is the encoding part of the unit. If you're doing things such as autoencoders, it works on the same principle of compression. So say you were using the unit to do an autoencoding of the values. This is kind of how Stable Diffusion works as well. What you would do is cut off the model at this layer and use these outputs, this output, as the input to the encoder. But you can look up more stuff on autoencoders if you think that might be something useful to you. And then from here, we notice that it gets blown back up gradually into something roughly equivalent to batch size by number of classes by 224 by 224. And we can also see that the model was frozen up to the backbone, among a few other bits. Now, I haven't included the results of training here simply because what you'll find is it's going to take a while and the outputs actually got wiped from here. But basically, when we deal with semantic segmentation, you're going to want to fit for longer because there's a lot more that you can train on, and it's very different in application than classification. So we're going to train for 10 epochs on our frozen backbone. We're also going to save here because what can very often happen is, remember how we had that batch size of 8? Sometimes that batch size of 8 is too much and you'll get a CUDA out of memory, even if it trains for an epoch maybe, especially when you unfreeze. And so you don't want to have your kernel crash or run out of memory, and you're not going to be able to save the model, because that is what winds up happening. So here we'll save. This commented out learn.load basically is just if you restarted the notebook, load back in our weights. Again, not shown here. Very annoying that it doesn't show it, but take my word for it. And this will be updated later to show it that it did pretty good. And then you'll notice here, we also do 12 at the unfrozen, because again, we want to train for longer. And this divide by 404 is again also based on Jeremy's notebook showing NLP training and gradual unfreezing. Now, this is all fairly similar fastai bits we know. Let's talk about the important parts we care about, which is the test data loaders and performing inference, because this also will be slightly different. So we'll create a test data loader and show a batch from it. And what we do to get predictions here is we're not going to use predict. We're going to use get preds, pass in the data loader, and wow, this is really annoying that it's not letting us look at the images. They all must have happened when I uploaded the notebook. So the shape of the predictions, as we saw earlier, will be batch, by channel, by width, by height. But when we look at our labels, we don't really want number of classes. We want this to be n by 1 by width by height with all of them in there. So we're going to bring back our argmax here on dimension 0. And this will essentially get those predictions and store it all into a single channel by taking the highest probability for each channel in there. When we're trying to save these results, however, we need to do some denormalization, which is essentially what's happening here. So we convert that prediction to a NumPy image, to a NumPy array. We're going to denormalize the values. That's what's happening here. Create a PIL image from this denoised or denormalized array, and we can save it as an image. Now, without the test data loader here, I've recreated how you would do this using the pipeline instead. And we talked a little bit about pipeline. We'll talk a lot more about pipeline in the fast core lesson, I believe. But basically, this is how do we remove at least the learner in this case when doing predictions. The second part of this lesson is going to revisit the TIM lesson from the original course with a bit more information on how fastai uses different pre-trained models in the vision learner and how you can sort of work with it. So far, we've looked at using the ResNet 34 model when using Vision Learner, but we haven't talked too much about fastai's custom head and trying to recreate it without fastai. This will be especially prevalent next lesson when we talk about deployment. And so today's topic is going to end on showing a bit about how to use custom pre-trained models and sort of getting you comfortable with the idea of how fastai does all these special like UNet learner or vision learner, where we saw that it would take a backbone of a model and do some custom bits to the front of it to get our new quote unquote model. So the first thing that we're going to do here is very quickly bring back pets and build the data loaders. Today's going to it's not going to be too long, but we're going to focus on just the model portion instead. So the next part is we're going to need the TIM library because fastai will use TIM in its vision learner now. So when you call vision learner, you can pass in the string to a TIM model and it will actually directly hook into TIM and get the model. Now, what is TIM though? TIM is a library by my coworker, Ross Whiteman, and it has a absolute outstanding number of PyTorch models that he's trained with his own benchmarks that include some state-of-the-art weights to choose from. In my opinion, it is more of an image model zoo for PyTorch than PyTorches themselves. Because on top of the fact that it is all of the weights, anytime a paper releases a weight, it's in there. If it's in TensorFlow, he will convert it into PyTorch. So it's exceedingly useful, and there's so many models in it. When you want to download a model from TIM, you'll basically do from TIM import create model, and you'll do create model, the model itself, and whether or not to download the weights. I've included a link to TIM's documentation down here to sort of help you understand what all this is doing, how the models are defined, and so forth. But for the sake of this lesson and the next lesson, just know that this is some of what fastai does under the hood. So we're going to go back to the vision learner for a moment and just make sure that we understand a few terms. So when we're dealing with the ResNets, for instance, we'll pass in our data loaders. Models comes from Torch Vision, and we pass in the ResNet 18. And some terms are defined here, but essentially the body is what we call the backbone, and the head is what we call everything above the backbone. I know I've reiterated this a number of times in the course, but this is a really important concept for you to understand how fastai works. Now, if we index into the model at the last part, we'll see that head, this custom head that fastai uses. It uses the create head function that adds in a few more linear layers as seen here and kind of down here. There should be one more, I would have thought, but it'll add batch normalization, some dropout, and most importantly, something it does differently is this two pooling layers, right? Which we sort of talked about last lesson. Now, if we try and look at the head of, say, the Tim model, vision transformer object is not subscriptable. This is a very common error that you'll see in fastai when you start trying to pass in custom models that say aren't supported out of the box. And fastai tries to, say, split the layer groups. The first index is no longer the head of the model because it doesn't start out like that. And a lot of times, it'll give you this type error object has no length if you try and look at the length of the model, right? Because here we can do length learn.model to body head. Try and do that with vision transformer, it's not there. And the reason for this is if you use models and you don't get this, it's because it's made out of NN sequentials, which is just a sequential list of layers that you can pass through. But not all models have this, and not a lot of them really do in general. And so as a result, you'll get this type error. I can't index into that because I don't know how to do it. So let's talk about PyTorch models for a second and sort of the types of them. Generally, when you define a PyTorch class or a PyTorch model, right, you'll use the NN module and inherit from it, define a few layers in the model, define a forward function that then will take some input and then have that forward function return the input going through all the layers plus any custom implementations and whatnot. But the key thing to note here is those layers aren't indexable, right? They're attributes instead. So if we were to redefine this as a sequential object, we can create a list of layers and then pass it into the super init. And because nothing special needs to happen in the forward, right? We don't need to modify this at all because it's just the layers. We don't even have to define it. It's just layers, pass it to the super, and we're done. And then when we create the model, index 0 is now that first layer. Index 1 is that second layer. So now we've had a brief introduction into NN sequential versus NN module. Let's bring it back to the vision learner, right? Because it's going to take this idea of NN sequential, and that's going to consist of the entire model's body and the entire model's head. So the body is everything up to the pooling layer, not including it, and then the head is the rest of it. But in the original model, typically it's just one pooling layer and the last linear layer. And so the body has those essentially removed, right? We talked about this a few lessons ago. However, one thing to note here is the fastai courses aren't really going to talk about this concept a whole lot of cutting the model, creating custom PyTorch models in the framework and such, because we're not really doing fastai now. Everything through here with these custom weights and bringing in custom models is all done in PyTorch. So to sort of visualize this happening, using PyTorch, I basically took the outputs from each model, similar to the learn.summary we saw a second ago, but this one doesn't require an input. That's why it's -1 here for the batch size. So if we take a peek at the diff, this is basically a diff of the body in a regular PyTorch model, you'll find that the adaptive pool 2D has been removed and the last linear layer, reducing our total number of parameters, right? This is something I've sort of mentioned a few times, but now you can actually see it visually. These layers were removed actually, and fastai just throws new stuff on it. So in order to create a body and head for a TIM model using the least amount of fastai we possibly can, let's see what that looks like. Now, fastai has a TIM body class, which creates a body similar to how fastai creates their bodies, right? By removing that pulling layer and that last linear layer. I've recreated them below. You're not going to find explains in these because we'll talk a bit more about it right now. But basically, the way to think about it is, so cut is what layer you want to cut at, right? We're cutting the model. So here, if it's an integer value, then we're going to create a sequential object of a list of all of the model's layers up to this cut. And the reason why we do this, and now actually I will include an explain tab in this because this part's super important. What this specific chunk of code is doing is it's taking our model that was not defined in an NN sequential, right? It's its own model, getting every single one of its individual layers. This is what children is doing and what list is doing as a result. And then where we believe that the layer cutoff point is, so it'd be -2 in this case because 2 above is where our pulling layer is. We'll make an NN sequential object of just those layers. And so this has now created a body for the model that originally didn't have anything we could subscript into. Now we can subscript into it completely if we truly wanted to. The other option fastai will let you do is use a function to cut the model. I'm trying to remember if I show a bit about that. But basically, the cut just needs to return essentially the same thing as NN sequential does here. So it should be a function that takes the model and returns only a chunk of it. Now, if we're actually creating the body itself, this is a very minimalistic version of what fastai does. So TIM models have something called a default config that we can get, and we should check if it needs pooling, right? That last pooling layer. And then we perform our cut. And then finally, if we need pooling before we output the features from the model, then we can return those, otherwise returning the model. And this is a very small version of what fastai does. Exploring TIM will give you some more ideas into what this is really doing and this is really doing. But the general understanding is, remember how I talked about autoencoders a second ago with semantic segmentation, where you could say, take the output at just say that last layer before we start blowing up and use that to pass it in as an input? That's essentially what this forward features does. So forward features would let us take the output from just this basic block without having to do, or with doing pooling, since it needs pooling. Yeah, it's something to definitely toy with, you know, starting to explore TIM. There's some, TIM is actually now part of the documentation set in Hugging Face, I believe. So I will include a link in the Discord to their documentation that you can read up on as you start learning about these. Because if you're doing computer vision, you should use TIM. And on top of that, I want you to get, of course, more and more used to removing fastai from it. Now, let's see. Yeah, so another way to think about the forward features is an encoder block. Now, the last thing to do here is we need to create a model. And what fastai will do is it will tell TIM, we have 3 input channels. and it'll tell Tim that the number of classes is 0. And this is sort of a little hack that lets us create a body from the model quickly, since we don't really care about classes, since we're just building a body right now. And this just sets the model to train. Now that we've created a body, right, this essentially encoder block, we need to take the output and turn it into classes. Now here, this particular model includes a pooling layer already attached to it. That's what this needs pooling is. So for our create head, we're going to take in the number of output features it has. Tim has this body.model.features, but basically this is the number of features that's going to be at the tail end of the model. We're going to take the number of classes we have, right? How many labels we want to have. And then because Tim includes the pooling layer inside it, we're not going to include a pooling layer in this case. And so now our head is basically this batch norm linear ReLU thing, ReLU setup. Now the other note for why we're not using pooling here is because we're using VIT. And VIT is practically almost like a tabular model in some cases. It's not a traditional vision model where we're using conv layers and, you know, this conv 2D setup. Instead, it's a transformer model. So it relies on, you know, transformers are language models. So it relies on this sort of 1D tokenized, I'm gonna say tokenized in quotes, input, or basically a one long array of the input pixels. So we can pass in, you know, we'll create a random batch of 2 by 3 by 224 by 224 pixels. And we can make sure that it all works by passing it through the body, followed by the head of our model. We can see that we have 2 predictions that have a size of 37 classes. Now, the last thing we need to do is we have this custom model, right? And when you create new models in PyTorch, you do what's called initialization. And initialization basically takes the model weights and sets them to some particular function operation. And research has basically shown that a good initialization is one of the most important parts of training a model, because with a good initialization, you can achieve better performance faster. And so fastai will use the chiming normal by default, and it's nn.init.chiming normal. So this is from PyTorch. And the apply init function will take our model, our head, and apply this init to it. Now, again, all of this is automatically being done under the hood with CNN Learner, or sorry, Vision Learner, but I'm just trying to peel back a few of the layers so you understand what fastai is doing. And if we look at the outputs now, thanks to this new initialization, the outputs are a little different. So we've made a body and we made a head. There's one other thing we need to get this working with fastai in the same fashion. No, that sentence is all wrong. There's one other thing we need to do in order to properly recreate how fastai handles models. There we go. Fastai knows how to split the model. And this is why when we were, say, training and we passed in 2 learning rates, the first learning rate would go to the body and the second learning rate would go to the head, also known as a split. So the first split and the second split. And so a split is basically just an arrangement of layers defined by some criteria. So in all the examples we've seen so far, a model was split into 2 parts, the body and the head. And then we froze the backbone, or the first layer group. right? That first group in splits. So for learner to work with splitting, or to separate our model from what needs to be frozen versus not, it takes in a function. And there's an explain tab over here to sort of help you understand what's happening. But essentially, you're going to create a function that takes in the model, and it's going to return first an L. And this L, here I index into the model. It can be model attributes instead. But this L is each one of our models, and specifically each one of our model layer groups that we want. So model 0 here is the body. Model 1 here is the head. And then the most important part about all of this is we're going to call .map params. And params is a function in fastai that lets it get the actual parameters for particular model groups. And this is needed because on top of the fact that, we can split a model and freeze it to, say, turn those weights into being untrainable, the optimizer also needs to know about these layer groups. Otherwise, we can't do bits like I just mentioned a second ago, where we have different learning rates for different layer groups. So under the hood, this is essentially being passed to the optimizer to tell it how we want to run things. And this isn't FastAI specific. All PyTorch optimizers, when you're using this sort of layer group functionality, operate in this sense. Now we can create a learner by making a NN sequential of our body and head, and tell FastAI I want our splitter to say the first group will be the first layer group will be the body, the second layer group will be the head. And this is just ignoring a lot of the output from learn.summary. But it shows us, okay, our total number of trainable parameters is 5.6 million, and our non-trainable parameters is 0. So the reason for this is when creating a learner, FastAI will call learn.freeze under the hood if it's a pre-trained model. Also, this should say vision learner and text learner. Tabular learner does not have a concept of transfer learning currently. But what we should essentially see is if we call learn.freeze, then we would expect our layer groups to work. And the total number of trainable parameters should go down and the non-trainable parameters should go up, which is exactly what we see here. So now we have the head of our model is the only part that's trainable. And the non-trainable part of our model, the body, is the entire rest of it. So from here, you can do learn.fine-tune, learn-on-freeze, and so forth. And what we'll find next class is how we take this custom model that we defined and take it over into deployment. And this is in the wrong thing. So we're going to talk about sort of deployment. How do you do inference with this stuff? And most importantly, how do you deploy without FastAI? Now, this one's going to be more of a live demo than just me showing and walking through it, because in this one, we're going to actually deploy to Hugging Face spaces. So in preparation for next week, what I would recommend is find a FastAI problem model, so forth, that you like, and take a peek at Hugging Face spaces. And we'll sort of together go through a real world deployment scenario using FastAI, followed by not using it. And I'll talk more about why we don't necessarily want to use it in lesson 5 and a bit in lesson 6. But that is the lesson for today. Again, I'm sorry that we had so many technical issues. Hopefully I can figure out what's going on weird with my webcam before the next lesson, because otherwise I might not even be able to have any meetings. But feel free to throw any questions you have in the chat and I'll run through them. One very good question is learn.freeze effectively turning on eval for the body layer? No, what it's actually doing is setting the requires grad argument for a layer. So if we go and open the code base here, I can quickly show you where this actually is coming from. So you can see in the base optimizer class here, I'll zoom in a little bit. This is the root class for FastAI's optimizer. And set requires grad here will essentially take in a parameter from the model and set this requires grad attribute. It's a function that sets it internally to either true or false. And this is what happens based on our layer groups. So eval is a bit different. Eval sets things like batch norm during training versus validation or during evaluate, which is different than requires grad. So hopefully that answers your question. Otherwise, feel free to put any more questions in the chat. I'll have the lesson 4/lesson 5 poll up in a little bit with the new category. And again, sorry, this lesson is a bit Otherwise, hope you guys have a wonderful weekend. Thanks for joining me.